So I was telling them, Austin, I want to spend a few minutes going through, well, I want to spend today and tomorrow going through the multiple choice and the FRQ from your progress check. And then I doubt I'll get through it all. So Friday will be spent doing the rest, and then your test is next week, okay? So I'll try to have the test printed out for you guys for next week when you come in on Monday. And then you can take, you know, you can work on it and finish up the multiple choice when you get home. So
we're doing the FRQ in class multiple choice.
Yeah. And I'll get that done for you on Monday. And then the people that are at home today, I'll try to get it printed out tonight so that they have it to take home with them. So
next week, Wednesday, I will try to be here on time, but I might be a little late.
Okay.
I'm doing the ice fishing thing for the egg group.
Okay. Just, I don't know, just, did you, oh, you were, okay. All right, so the first question here, it says so I want to go through these. I also want to talk to you guys if we have this, and they're still determining what we're going to do about the exam, if it's going to be in person or not. But the multiple choice, you don't get to use a calculator on, okay? So they give you problems on here that you can do without a calculator, but you have to be confident, a little bit of confidence in your ability to not have a calculator, okay? So we're going to talk through, I want to spend some time talking through like strategies for answering these multiple choice questions without a calculator, you know, trying to sharpen up a few of your skills for multiplication without a calculator, like multiplying decimals and stuff like that, and show you a few tricks for eliminating items on here and why you would do that. Okay, so this is more a skills-based lesson. You know, we're going to talk about equilibrium, but it's as much a lesson in how to take a multiple choice test for AP Chem as anything. Okay, because I don't know that I've spent a lot of time going through that with you guys since we've been in this back and forth kind of thing, and I haven't really given multiple choice as much of a nod as maybe I should, and so that's why I want to spend some of this time going through that. All right, so here we have a graph, and they're saying that we have the decomposition of N2O4, and we're going to be having N2O4, and we're going to be making NO2. Now, how do I know that this is getting made and this is getting decomposed? Well, because I started out with some of this, and I didn't have any of this to begin with, okay? So I know that this is going to be my product. And I'm going to answer the question based on the graph, what time is equilibrium established? Well, remember, equilibrium is not where they're equal, so do not pick B, okay? We want to find a time where they're still making this and they're still making this, but that concentration has leveled out. So the answer for this one is going to be D, okay? And a lot of times they'll give you like an A, and a D, and a D, and then you've got to be able to pick between the different things here. So kind of, you know, then you can eliminate like two things at one time, okay? Yeah, yep. And we'll see some of those here. Now, the answer key that I sent you guys for this, it's a little out of order. So just realize that answer key, you have to go in like 3 problems before you get to this, so that it's off by like 3. But after that, it's all completely in order.
Wait, was this the progress check from like a week or so ago?
I posted it yesterday.
Probably later in the day would be my guess.
Yeah, after 6th hour.
Okay, sorry, then I missed it.
Okay.
I usually check it all in the morning.
Yeah, well, a lot of times what I do for your class is I'll record that 6th hour, and then I post it after that 6th hour because I don't want to have to teach twice. I'm lazy. Sorry.
It's understandable.
All right, the next one, we've got acetone in here. We're placing it in a container. It's going to be sealed, and the container is allowed to sit for a few minutes. At the end of 2 minutes, some acetone liquid remains in here, and they want to know which best describes the data that's present here. Okay, so this is a KP situation, so we're looking at pressure here. And we can see that when we get to this point, that pressure has started to maintain a constant value. Okay, so the acetone heats up over time, causing more of it to evaporate. Well, they didn't say anything about it heating. There's nothing here. There's not a hot plate. There's not a Bunsen burner, anything that's happening there. The other thing is that if the temperature changes, your, well, I guess that doesn't matter in this one. This is, never mind. Let me take that out. So I don't think that this is valid. Okay. They're not mentioning anything about a temperature change. So I would eliminate this one. The acetone has completely vaporized. So has it completely vaporized if liquid remains? No. So get rid of that one. The acetone vaporizes from liquid at a constant rate, and the rate of condensation increases until it becomes equal to the rate of evaporation, and the pressure is constant. That sounds, well, we're going to keep that one for right now. We're going to just double check this one. The acetone vaporization from the liquid vaporizes from liquid at a rate that is fast in the beginning, but then slows down until the vaporization process stops completely. Now, is this still exchanging between here and here? Okay, then we haven't stopped vaporization completely. So we're going to go with C here, because none of the rest of this makes sense. Okay, questions on any of those? All right. You guys might want some paper out to like try some of this math with me and stuff that's coming up. Just to, I don't want calculators though. We're not going to use calculators. Well, you might want a calculator just to double check your, but I want you to try it without a calculator first, because you need to start building that confidence that you can do this without a calculator. In most normal years, you would have started back in September taking multiple choice tests for me. You do not use a calculator in here in multiple choice tests most years. Okay, this has been an exception. So you haven't got that confidence built up yet. Not for calculator. No, I would let you use a calculator, but I wouldn't let you use a cheat sheet, a little note card. All right. Sample, I don't tell you about the no calculator thing in AP until you're already in here, because otherwise you might not take the course.
Hey, that's fair. That's fair.
I'll be honest with you. I keep that one. I keep that card, kind of hidden.
Oh, I didn't tell you guys about that. I thought I did.
Well, the thing is that they don't make the questions to where you can't answer them without a calculator. So you have to build your confidence that they're not going to do something that mean to you. And it's not hard math. It's like 2 times 3 or move a decimal point. I'm going to show you some tricks. So it works out. Okay. All right. So sample of this is in a sealed tube. Okay. It 20 degrees is placed in a temperature bath at 30 degrees. So we're increasing the temperature here. Observations and changes in the color, blah, 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 function of time. Which of the following is an observation that would best support the claim that the reaction present above has reached equilibrium? The total mass of the system remains constant because at equilibrium, the amount of reactants and products don't change. Well, are we gonna, our reactants and our products, they're like, that's gonna remain constant anyway. We have the conservation of mass law. So I'm getting rid of that. Color of the system changes from brown to completely colorless because at equilibrium, only one product will be present. No, because we can have both of these things present. It's just which one do we have more of, okay? Total pressure of the system decreases, then reaches a constant value because the equilibrium, the amounts of the reactant and product no longer change.
No, it's a sealed tube.
Oh, I was looking at the picture below it.
There, is that better?
Yes.
Okay. Yeah, it's a sealed tube.
Okay.
Okay. Okay, so that's plausible. All right. The temperature of the system remains constant because at equilibrium, the temperature must be constant. Well, they said that it's, okay, so there we go. All right, now we're at this beaker. Okay. So when AgCl is placed in water, it's going to dissolve. And it's going to dissolve according to this equation. The particle diagram above was proposed to represent an aqueous solution, and it's in equilibrium with its ions. Which of the following best describes whether or not the diagram provides a good representation for dynamic equilibrium at the microscopic level? Okay, the first one is it's a good representation because it shows that the dipoles of the water molecule are oriented around the silver and the chlorine. Now they're talking about dynamic equilibrium here. Okay, so that what dynamic equilibrium means is that some of this solid is going to go out here and become these ions, and some of the ions are coming back in and redepositing back into the solid. So we've got that exchange going on. Is this showing that exchange by having the water molecules around these things? No. So I'm getting rid of that. It's a good representation because it shows that the concentrations of Ag and Cl are equal at equilibrium.
Doesn't show us that.
Well, yeah, they're equal. 1, 2, 3, 1, 2, 3. But does that indicate that we've established equilibrium? No. Okay. It's not a good representation because it doesn't show that the concentration is constant at equilibrium. It is not a good representation because it does not illustrate dynamic equilibrium in which the rates of the forward and the reverse are equal. Well, at dynamic equilibrium, does that mean that the rates of the forward and the rates of the reverse are equal? Okay. And so we've got to go between these two. So do we need to show that the concentration is constant at equilibrium? We are not able to show that, though. We need to show that, but we're not able to show that because we don't have anything to compare it to. We don't have another diagram over here showing us that this was the same amount of, you know. So that one's out. So it's D. All right, next one. Here we have a particle diagram, and it's going to show a system. We've got this equation going on. Which of the following explains whether the particle diagram indicates that the system is equal? Is at equilibrium? The particle diagram does not illustrate that the system is at equilibrium because it shows that the system only at one point in time. The particle diagram does not indicate that the system is at equilibrium because the ratio is not equal to 1. Okay, that doesn't matter because our ratios here can be vastly different. When we've seen KSP values that are equal to 10 to the negative 90 something, right? So that wouldn't have a ratio that's 1 to 1. So we're getting rid of that guy for sure. Particle diagram indicates that the system is at equilibrium because the value of K is small. Well, exactly. But you can tell that K is small, okay? And I just want to, well, can you? Let's see. We've got 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 products. So we've got 10 of these. We've got 1, 2, 3, 4. Oh, I counted that before, didn't I?
No, so you were going to.
1,
but you
2,
got-
3, 4. Okay, so yeah, 4 for that. So that's like saying 40 for our concentration on the bottom. And then the top, I've got 1, 2, 3, 4. Okay. So if we were to look at that, right, our K value would be small. Okay. And I wanted to go through that with you so you could see how you could get a K value, from, you know, because that might come up. They may, because they like their particle diagrams. Now, we don't have one of those in this packet, but I could see them throwing something like that at you. That makes sense? Also, this down here would need to be squared. No, I'm sorry. We would have had 160 on the bottom, right? Because this would have been squared for the X. No, that would have been 100. Because I had 10 for these, right? I had 10 dots, so that would be 100 on the bottom times 4 over, and then, oh, no, not 4, no, because it's a single here. But the 4 on top would be, which would be 16. But you'd still have a small K value, okay? But I could see them doing something like that, okay? That would be perfectly valid. And they might ask you, you know, like, what is your K value? Is it greater than, less than 1, equal to 1? It can't be determined, okay? So those would be your 4 options. All right, getting back to this. So yeah, we can determine that it's small, but we can't determine that it's an equilibrium because we don't have another picture over here to compare it to. We don't know that this has maintained its concentrations. So we can't really tell that it's at equilibrium, so that gets rid of these two. Okay? So that leaves you with A. All right, moving on. Okay, so here the particle diagram is going to show changes that occurred. We've got equal molar mixture here of X and Y. So we had these two things came in. We had an equal concentration of equal molecular mixture. Which of the following statements best supports the particle diagram? So X is here, Y is here. So I've got 1, 2, 3, 4, 5, 6, 7. So I've got 7 Y and X. Actually, I should probably put X over here and put this one. I got 0 of these here. And then over here, I've got 1, 2, 3, 4, 5, 6, 7. So equal amounts, they said that. So it makes sense. Here, I've got 1 of these. So now I've got 1, 2, 3, 4, 5, 6. And then I would probably have 6 of these. 1, 2, 3, 4, 5, 6, 7. Oh, I got 7. How do I have 7? 2, 3. Oh, I counted them. Okay, then that makes sense. Okay. So 6, 6, 1 here. Here I have 1, 2, 3 of these. And I have 1, 2, 3, 4 of those. So I should have 1, 2, 3, 4 of those. Okay. And then over here I have 1, 2. I have 2 of those, and I have 1, 2, 3, 4, 5. Okay. So the rate of the reverse reaction this way is 0 because the concentration of XY keeps increasing. Does that mean that if we're increasing this, does that mean that we're not forming any of these things? No, it just means that we're forming these things at a slower rate. Gone. The reverse reaction has a higher rate than the forward reaction? No, because we're actually forming more of these things. So that one's out.
Oh, wait, I have a question. Would it technically be higher because there's more products that it can reverse back to?
But it's still making more products because they're increasing. It's still making more products than it is the other one. The forward reaction has a faster rate. So the reaction this way is faster than the reaction this way, between 0 and 300 seconds, because more products are being formed, which was my argument.
Please excuse the interruption. Would the following students please come to the Student Center? Leonardo Duran Arambula, Mickey French, Sydney Gunther, Lillian Coker, Sean Cranenberg, Rachel Luckett, Joseph Martinson. Please come to the Student Center.
The rates of the forward and reverse reaction were the same after 100 seconds because the rate of formation of XY was constant. Well, that is not the case. Okay, we went from 0 to 1 to 3 to 5. It's not constant. So that guy's gone. Any questions on that one? When I'm counting these molecules up, you're going to be able to mark on your stuff. I always try to do that, like mark through them, because then that way you try to avoid mistakes with count, double counting and stuff like that. And you can mark all over your test. Mark it up. All right.
Can you do that on the AP test itself?
Yeah. It's your copy. Yep. You paid $100 for it. Mark it up. All right. So in an experiment, we've got pure HI being put in there. So initially we didn't have any of these. At the table above provides the initial and equilibrium concentrations based on the data, which value for the KEQ for the reaction Y. All right. Now I notice that I have, this is in a 1-to-1 ratio. Okay. So that means I didn't start out with any of these things. It said that all I started out with was this. So that means that if I made this much H2, how much I2 should I have made?
The same amount.
Same amount, exactly. So I can put that down, and I know that the I2H2 is going to be equal at equilibrium. Okay? Now, do I even need to calculate the KEQ? No, because that's the only option that they've given me where those two things are equal. Did I need a calculator for this? No. Okay. Did it look like I was going to need to?
Yes.
Yeah, but you don't. Okay. We can get by without our calculators. I promise you guys, we can't. All right, let's keep going. We've got SO2 here. It's going to react with Cl2. It's going to produce, and I need to get that down so Austin doesn't get confused by that bottom picture. Okay, we're going to react. We're going to produce SO2. So we're making this stuff. We've got a mixture of 1 ATM of this guy and 1 ATM of this guy. Are going in.
A 1-to-1 ratio?
Yeah, they're in a 1-to-1 ratio, and they gave us 1-to-1 pressures here, okay? We didn't start out with any of this. So the table below is going to show us the initial partial pressures of each gas and the equilibrium partial pressures of each gas, okay? So what is PCl2 going to be equal to? Yep. And remember, these are partial pressures. So what should they add up to be?
100% of 1.
Okay. So we know that that guy has to be 2 ATM or 0.2 ATM. So that either gives us C or B to deal with. Okay, so that has helped us. Now, look at this. This value is less than 1. This is greater than 1. Okay, so if I set up this equation, I'm going to have 0.8 on top, and I'm going to have 0.2 times 0.2 on bottom. Okay, is this value going to be greater than or less than 1?
Less than 1.
0.2 times 0.2 is what?
.04.
I believe it's 0.04, right?
And then if you do
0.2 times 0.2 is 0.04, and then 0.8 over that.
Oh, I was thinking multiplying everything together.
Oops, shoot, sorry. 0.8 over that,
Would be
bigger than 1.
Okay.
So that means that our answer is going to be C. We don't need to calculate. We don't need to calculate what that value is. Okay, we don't need to go through any fancy math for that. We can see that that's going to be greater than 1.
Mm-hmm. So let's say the 0.8 was there, then it would be B because 0.2 times 0.2 is less than 1.
Yeah.
Yes. Okay, so when you're multiplying all together decimals, they become smaller.
Yeah.
When it's decimal times decimal, it's bigger. When it's decimal times whole number, it's smaller. Right?
Well, no, because this is 0.2 times 0.2. That's going to get smaller.
We're dividing them.
Yeah.
Okay.
Yeah, dividing gets them bigger. Yep. Okay, better? Good?
Mm-hmm.
Okay. Like I said, you've got to kind of pick up a few tricks along the way, but you can do this without a calculator. Straight up. I did it to verify that I was doing it because I was thinking I'm like 0.04, but then she made me second guess myself. So.
But you made you second guess yourself by saying it was 0.04.
Do you want to go to Mr. Phillips' office? I feel like you do. I just have that feeling. He came in today and did my final walkthrough for the year. We have to get observed a couple times a year. I think he might have been in one of your classes at one point for one of the labs. Yeah. So I'm done with that. That's off my list for the year now. Every year we have to, or every third year we have to get observed like 3 or 4 times. And so this was we call it on cycle. So this was that year. I should only have maybe 2 more times that I have to go through that before I retire. Maybe just once. No, probably twice. All right, anyway. So diagram here, we're looking at this. We've got 2 isomers. What is an isomer again? Let's just go over some vocab. Everybody remember what an isomer is? I want to give it a go. What's iso mean? You should know that as a prefix. Isotonic? What did that mean back in biology? Iso means the same. So what an isomer is if we counted up these carbons and hydrogens and everything here, these would have the same formula, molecular, but they're different. Okay, this guy has these up here, off to the side. This it's diagonal. Okay, so they have the same chemical formula, but they don't have the same structural formula. All right. Several of your disaccharides, your glucose, sucrose, some of those, no, glucose and fructose. Anyway, some of the simple, the monosaccharides and disaccharides have the same chemical formula, but different structural formulas. Just set up differently. React, yeah. Yep, it does. All right, so they're set up here. We've got, they're in an equilibrium mixture of the 2 gases at that temperature. The concentration of the cis is in the second vessel is twice the concentration in the first vessel. So we've got one vessel here that has 2x of this versus another vessel where it's 1x, okay, for the concentration. So I'm going to put it in square brackets to remind myself that it's concentration. What is the concentration of the trans 2-butane? So the other guy here. What is he going to be in the second vessel compared to the first? Okay. So, no, I have these reversed. This is supposed to be 2 times, and this is supposed to be 1. Make sure I got that vernacular written. So the second vessel is twice the concentration. Sorry about that. Okay. So they want to know concentration of the other guy here. Okay. So if these are in a 1-to-1 relationship, which they are, because we don't have any coefficients in front of here. Okay. If we ended up doubling the concentration of this amount, what would happen to the amount of this? Would it half it? Okay, we're at equilibrium. Remember that K equals, okay, let's just say that K equals 1. All right, so that would mean that this would be 1 over 1, right? Our products over our reactants. Now over here, remember we haven't changed the temperature. The temperature is the only thing that's going to change K. We are at equilibrium. So if we are now at 2 for our cis, which is the bottom, what would the top value have to be here? 2. So if we double that, it's going to be what? Twice. Did I need a calculator? A lot of your AP Chem comes down to logic, okay? Logic with a little bit of chemistry understanding, okay? But a lot of logic. That's what it is. So if you've enjoyed those logic problems over the years that you've gotten stuck with, you'll do well with these tests, okay?
For a second, I thought you were going to say lucky guessing, the second one.
Yeah, but you've got to, I mean, you're not going to guess your way through this, you know? I mean, you've got to have some, because, you know, there's some things that are just counterintuitive too, like equilibrium. You know, equilibrium, your gut reaction is everything's equal. And we know that's not the case. Okay? So, all right, let's look at the next one here. You're going to I got to go to my sheet here. All right. Equilibrium here, we've got 0.1 molar HBRO. So 0.1 molar here. It's represented with this equation based on the magnitude of the equilibrium constant. So this, okay, which of the following correctly compares the equilibrium concentrations of the substances and why? This tells me that what's going to be favored? Products or reactants? This is a negative value.
Reactants.
Reactants. We're going to have more of this than we are this guy. Okay? So the equilibrium concentration of BRO will be much smaller than the concentration of HCO. So these are both products that we're talking about here. They are both in a 1-to-1 ratio. Is one of these going to be smaller than the other? No, get rid of that. The equilibrium concentration of BRO will be much smaller than this because KEQ is very small compared to 1. Well, that sounds pretty good. That sounds pretty promising, right? Based on what we just set up here. Equilibrium constant of H3O plus will be much smaller. So this guy will be much smaller than this guy. Nope, we eliminated that on A. They're just staying the reverse essentially. Equilibrium concentration of H3O plus will be larger than this guy. No, This guy's going to be bigger. So B is our answer. All right, next one. We've got a certain temperature. So at a certain temperature, these are going to react. We're going to produce SO3. And they evacuate a rigid vessel. It's originally filled with our reactants, each with a partial pressure of 1 atm. Which of the following is closest to the partial pressure of O2 after the system reaches equilibrium, and why? Okay, well, we have a Kp value of 2 times 10 to the 5. So what's going to be favored here? Our products or our reactants? Products. So we're going to have more pressure over here and less pressure over here. These values are going to be less than what? 1. Because they started out at 1. We know that they're going to get smaller because this value is greater than that. Plus, I mean, they would have to get smaller just because we are going to produce some of this. Okay. All right. 0 atm. Because Kp is large, nearly all of this is consumed before the system reaches equilibrium. We're still going to have some of this there. This isn't a massive number. I mean, it's big, but it's not massive, okay? So I'm going to hold off on that. 0.5 seems plausible as well. It's very large. Nearly all of the SO2 is consumed, but an excess amount of O2 will remain because we're using this at 2 to 1. Okay, so we're going to use up this faster than we're going to use up this because we had an equal amount that we started in at. Does that make sense? So if we use up all of this, that would take this down to about what? It started at 1. If we used all of this one up, how much of this would we use up? Half. Well, that's looking pretty darn good then, isn't it? Okay. We know it wouldn't be 1 atm. Okay. We know that O2 wouldn't be at 1 because we know it's going to be less than that. So these two are completely gone. So that leaves us with this. Did I need a calculator?
No.
All right, next one. We've got a 0.1 mole sample of zinc. It's getting added into a 500 ml container of 1 molar CuNO3. We're going to let it sit overnight, and we're going to observe it the next morning. Okay. Almost all of the zinc will still be in the beaker. Well, look at this K value here. What does that indicate? Right, we're going to lie heavily over here. So will we still have a lot of zinc in our beaker? No. Okay, half of the zinc will have disappeared. Does that sound right? With this large of a Kp or KEQ value? No. Even 2/3, does that sound valid? No. So we're going with that. Yeah, almost all of it. I mean, that is a massive number. Now, you know, maybe this guy up here, we could maybe possibly make an argument for 2/3, probably not even then, but a 10 to the 37, good Lord, okay? All right. Next one's 13. Okay. So here we're looking at, we've got these 2 half reactions. We're trying to build these half reactions so that they look like this. Okay. So what I need to do is I need HA on this side, which it already is here, but I need HB to get flipped around. Okay. So this equation needs to get flipped around. If I flip that guy around, then I've got HB minus plus H plus yields H2B. Okay, so I'm going to get rid of this. When I get rid of that, I'm going to take this and I'm going to go 1 over that amount. Because remember, when I flip the equation, I got to take the reciprocal. So that's going to take my H plus, and it's going to get rid of this H plus, because those are going to cancel out. And that will give me my HA here. It'll give me my HB here. It'll give me my A minus here and my H. So then I'm good, okay? So what does that equal? That would equal K1 over K2. So then we just look for that, and right there it is. Yay? Nay? All right, next one. Same idea. Trying to flip things around, figure out how this is going to work. We're trying to make this equation. Sorry about the subscripts, superscripts. You guys can function though, I think, right? All right. So our PbCl2 is right. That's okay. But this guy right here, I need to flip him around. So that means K2, I'm going to have the reciprocal of that. So I'm going to have K1 over K2 now. K1 over K2. And then, oh, yeah, that's the other thing. This one of these.
If you flip the second reaction, it would be 1Cl to 12 on both sides.
Yeah, just one. So I've got to multiply this by 2, which means that I need to square this. So that ends up being D. Good?
The bell is gonna ring.
Yeah, 1 minute warning.
I was on a roll. But did I need my calculator at all?
No, not at all.
I want you guys to go home tonight. I want the rest of your multiple choice at least done tonight. So when you tune into my discussion tomorrow, you're ready for that. And then if I start in on the FRQ tomorrow, then stop the video, do the FRQ, and then go back to my video. Okay?
You're definitely gonna record.
Oh, yeah. I've been recording it every day, except yesterday wasn't pretty. I ended up having, I fell apart on the last question, and Renee McCormick, I ended up pulling up her video because I couldn't get it together. I had a really, 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 really bad Monday here. I wasn't in trouble. I did everything right, but it was still just kind of rough on me, and I was still kind of in this recovery phase yesterday. And my brain just was,
Yeah.
and so,
It happened.
yeah. So anyway, yes, I had all good intentions of recording yesterday. I actually recorded, and then it was just so bad that I could not post it. I just couldn't do it. So I'm like, go watch Renee McCormick. She does a better job anyway. You still get the good Southern accent. You know, she's better at the accent than I am, and, you know, she's good. Bye, y'all.
Bye.
See you next week.
Yes, we will see you next week and in class on Friday.
Yep, I'll be here. My arm isn't too sore.